Alright, let's look at the homework 11.9, problem number 6. Alright, so we want to find the power series representation for this function. Alright, so let's do that. Alright, so first thing is I'm going to rewrite this function as, right, so it's using one of the log properties. We can write it as natural log of 1 plus x. Alright, so it's division, so we can write it as a minus natural log of 1 minus x. Alright, so I don't know what to do directly from here, so I'm going to take the derivative. So f prime of x is equal to, alright, so derivative of natural log of 1 plus x would be put 1 plus x on the bottom and derivative on top. Right? So minus, and the derivative of natural log of 1 minus x would be put 1 minus x on the bottom. Derivative is negative 1, so I'm going to turn it into positive 1. Alright? So we actually know what to do with this guy. So here we can rewrite this guy as 1 over 1, so this is a double negative trick, minus negative x, right, and the plus. This guy we know what to do directly from here. So 1 minus x. Alright, so the power series for this guy is going to be a summation. N approaches n from 0 to infinity. Then this is going to be just a negative x to the nth power. Right? And the power series for the second term would be a summation. N goes from 0 to infinity, x to the n. Right? Then you would have this. So we can put them together. So it's a summation. N goes from 0 to infinity. Right, so this is going to be just negative x to the n plus x to the n. Right? Then if you look at this, if n is even, then this is going to be just x to the n, because negative 1 power, negative 1 to the even power is going to be just positive 1. So you have 2x to the n. So, but when n is odd, then you have a negative x to the n and a positive x to the n. They cancel out. So what you end up getting would be n goes from 0 to infinity, right? You would have 2 of x to the 2n, because when n is even, then we have 2 of those. But n is odd, they cancel out, so you just get that. Alright, then if you want to find the original function f, all you have to do is take the antiderivative of that power series. So if you take the antiderivative of the power series, summation, n goes from 0 to infinity, 2 x to the 2n, and with respect to x, and this is going to be equal to, right, so you still have a summation sign, so summation, n goes from 0 to infinity, right, so antiderivative would be just a power rule. So you have x to the 2n plus 1 divided by 2n plus 1, right, and plus some constant c. Right? We can find that this constant c by looking at f of 0. Right? So f of 0 is, if you look at the power series, if you plug in x equals 0, this whole thing is equal to 0 except for c. So we have that. but the original formula is natural log of 1 plus x over 1 minus x. If you plug in x equals 0, you get natural log of 1, which is 0. So we actually know that the c is equal to 0, right? So we found that this is actually equal to 0. All right, so then we have a power series. So it's going to be, I'm going to actually put 2 here. Then you have x to the 2n plus 1 over 2n plus 1. All right, so let's type it in, see if it's correct. So you have 2x to the 2n plus 1, then divided by 2n plus 1. Right, so let's submit for testing. All right, looks like we got this one correctly. All right, graph the f and the several partial sum and on the same screen. All right, let's bring out GeoGebra here. All right, and we're gonna just define the function. So function was f of x is equal to natural log of, all right, 1 plus x over 1 minus x. All right, so we have this graph right here, and I might just change the scaling a little bit so you can see it better here. So we have that, and then I'm gonna do the partial sum. I'm gonna call this a partial sum g of x is equal to, oh, actually before we do that, I'm gonna actually make a slider. So here, slider. All right, and I'm gonna call this capital N. All right, and the capital N is just a number of terms we're gonna add up. So I'll just do say 0 to 50, and the increment is probably by 1. All right, then put a slider there. So I'm going to define g of x as summation, so sum. Right, so let's see, actually, so cap of sum, right, then it's going to be, so expression is going to be, let's see, 2 times x to the 2n plus 1 and over 2n plus 1, right? Then variable is n, and the starting number is 0, and the ending number is this capital N, so that we can use the slider to change it. So I'm gonna hit enter here. All right, then what we do is this. All right, so you can see that this is in purple. All right, so maybe I'll change the color here. So if I right click and go to object property, all right, so I'm going to use probably something, so how about red, right? So I'm going to turn it into red. All right, so red one is the approximation, and the blue one is the original function. You can see that they are kind of similar along the about the origin, but as you go far away from the origin, these two functions are very different. All right, so what we're going to do is we're going to add more terms. All right, so right, capital N equals to 2. All right, so look, got a little bit better, and you can see that as I increase the number of terms we add up, and the function is getting closer and closer and closer and closer and closer. All right, so we have this picture. All right, so let's see if we can answer the next question here. All right, so graph f and several partial sum, and which one looks like the one we have. All right, so it looks like we have this one, right? So we click on that. And what happens as n increases, right? So that's, we're talking about capital N here, right? As capital N increases, partial sum approximates f better on the interval convergence, which is, all right, so we haven't really computed the interval of convergence, but you can see that this is going to be between. So say I'm going to put the x minus 1 here. So this is x minus 1. And also x is equal to positive 1. All right, so you can see that it's going to be between -1 to positive 1. All right, so we can answer the next question, which is between -1 to positive 1. All right, so let's submit for testing. All right, looks like we got the graph correctly and the interval of convergence correctly. All right, that's it. I hope that this was clear.